And I will guarantee you we'll be back on schedule because we already talked a little bit about the grippers this morning. We talked about grippers being part specific and the challenges going up. And for so many of these challenges that I talked about this morning, higher mix of product and so forth, that conventional grippers just aren't meeting the need. And yet we think that with flexible grippers, we can meet that need, and as we said this morning, enable growth. I want to stress, as I said this morning, that this is not the solution. Replicating the human hand is not the solution. There's a lot of, I think, brilliant scientists and engineers who have wonderful designs to do this, but in the end, it's just not, it's not cost effective, and for every degree of freedom that you add to any device, there's a multiplicative effect on reliability and lifetime. I think the better approach in gripping is to limit the degrees of freedom, just enough degrees of freedom to do the tasks. And a company in Boston, technology I believe came out of Harvard, is a good example of that, where they use this, again, pneumatic adaptive gripping approach to operate in a fairly broad range of product handling. So let's go into these four areas, at least four areas: self-adaptive, jamming, Bernoulli and needle, and electroadhesion. Again, I'm the founder of Grab-It, but I like to give these presentations beyond my company and try to help us all with what else is going on in the industry. I think before we start, though, there's a lot of benefits in a lot of these new technologies on flexibility. Many of them are low energy. Good example is electroadhesion. We operate literally at microamps of current, very high voltage, but microamps of current. So that's actually 3 orders of magnitude less energy than conventional air compressor driven vacuum grippers. But there's trade-offs as well. You want to be careful on your grasping and release times, holding ability. And this is where, again, we think, as I said this morning, low-cost sensors and being able to combine that sensor technology into a learning database to optimize that robot motion, to meet these challenges. So let's start with self-adaptive grippers. This is information from a company called Robotique out of Canada. They've come a long way with parallel grippers, grippers that can surround the product. It is, in my opinion, a step forward in flexibility. It's by no means the gripper that can handle single gripper handling 1 million SKUs in an Amazon warehouse, but it's come a long way. It has a programmable stroke in the fingers. The fingers, as we said, are adaptive. They do have force control. And I'm sure they would be extremely interested in the technology from SensorBrate that we heard this morning as well. I think that they'd be extremely interested knowing those guys. And grip detection, exactly what we heard about from SensorBrate. So they're out there getting some very interesting applications, and I just have this video for this 2-armed robot with these Robotique self-adaptive gripper, just handling different parts. Yeah. And I'm not sure where, but they. It is I believe it's a furniture manufacturing operation. So one example. Another example is handling cables and making connections. Video quality here is a little limited, but again, you can see some little more dexterity here than what we've seen in robotics. Yeah, it's the. Is that right? Yeah. Anyway, We looked this morning at jamming technology, just for those who are not familiar with this new technology. That sounds like we have some experience already in the crowd with the jamming technology. But it basically uses compressed air to surround a part. Once the part is surrounded and encompassed, the air is taken out, and it holds that part in place. In my opinion, the advantages of this technology is extremely flexible for three-dimensional parts. The disadvantage is if you just look at the space required to get this part, look at all this other space around the part. So if you've got parts tightly stacked, and bin picking as an example, I think they got some challenges. Would you agree, Walter?
You know what the biggest disadvantage is for my case. I'm an automation guy. I was working with Google for 10 years, and I say I have no part tips. I didn't know whether I have the part or not.
Yeah.
So and this is why this company, and they're selling this, but really successful in automation. It's not possible because you need to be sure that you have the card, and you need to know how much force you apply to the part already.
For the tests that we did, you can kind of cheat because it put a cross and we know the gripper really land right there.
Yeah, that's interesting. At Grab, we'll talk about Grab's technology in a minute, but one of the things that I like about using flexible circuit technology is the same flexible circuit on the Grab-it gripper that is creating the electrostatic force can also be used as a capacitive sensor. And we can also, when we are grasping something, albeit we might be at microamps, but there's more amps than we're not grasping. And so there are ways of inherently detecting without adding sensor cost. And you're right, in this technology, I don't see anything inherent that they would have to add technology like we heard from SensorBrite. But anyway, this technology came out of Cornell, I believe, and it was licensed by Empire in New York. And this is Walter's Bernoulli and needle combination. I'll just turn the presentation over to you, Walter.
It's nice to see you.
So Schmalz, as you heard earlier, has extensive experience and success in automation and grippers. And I heard the name Schunk. In my opinion, take the two leading robot gripper companies, it's Schmalz and Schunk, and maybe Robotique will be there someday. But this was interesting, doing a kind of a hybrid approach. The needles being able to ensure the handling of, as we heard, fabric. Now, electrostatic, we'll cover just so we all understand how we work. This is a gripper, and as you saw at Grab-it, we started in the two-dimensional world. We said, all right, let's get the low-hanging fruit, and let's just get two-dimensional parts. So that's where we started. So like this flex gripper, or this flexible circuit, the gripper itself is a two-dimensional product. We apply voltage to the gripper. It applies charge on the part, and then we match up. The beauty here is the strength of electroadhesion is a function of the conductivity of the material and the amount of contact surface. And so if you have a compliant surface, then you can get this curved surface compliant with the gripper and maximize the contact surface to get good gripping strengths. The reason I bring that up is this technology of electrostatic force is not new. It's been around in electrostatic chucks in the semiconductor industry for many, many years. The difference there is you're handling silicon wafers extremely smooth, and you're handling and the gripper's electrostatic chucks extremely smooth, and the two smoothness is what gives them the surface. But what we say at Grab-it is most of the world is not smooth. Most products are curved, and even they look smooth. If you put them under a microscope, you'll see curved surfaces, and that's why the Grab-it grippers have this compliant technology to comply to a lot of different parts. And as we said, also we can add vision to light the background to get the orientation of the part. And we saw these this morning. So here's another point that I think is important about the gripper, and Walter knows this as well as anyone. A lot of people start with the robot. They start with a 6-degree freedom robot, or maybe some of the new 7-degree, 12-degree, 14-degree robots. That again, the ultimate in flexibility. And then the last thing to do is design the gripper. So I think if you start with the gripper, if you look at the products that you have to handle and start with the gripper and design a gripper, you can then go back and have a much simpler robot. And I'll give you an example. This was our first installation in China at Gravitt. And we were simply getting fabric, this is collars that go onto shirts. We were simply destacking these, and they tended to kind of stick together, and we had to destack them. And once we had the gripper designed to do that, this is the Gravitt gripper, we only needed 2 degrees of freedom. All we had to do was go down and get this, lift up, move, and put it on the takeaway conveyor. And that's what you see. Let's see if I can get that video going. Okay, it looks like there we go. You see, we go over, that one gets taken away on the takeaway conveyor. But this is extremely low cost, 2 degree freedom pick and place device. You don't, because of the capability of the gripper, the approach with the gripper, we didn't have to go with an expensive robot. The exciting thing is this gets duplicated for us potentially thousands of times. And so it's because one of the things we've done is met the economics by going with a very low cost pick and place. All right, so then we talked a little bit about this morning. The next step for Gravitt, not yet, we're not doing this yet, is 3-dimensional parts. And I've talked a lot today about each picking, the challenge of one gripper handling a broad range of parts based on vision input. The thing that I think I'd like to stress here is the flexibility. That same gripper that was doing each pick is now handling fruits and vegetables. In fact, we think this is probably maybe the best place to start. We heard Cameron talk about strawberries, so I think maybe. Yeah, well, I'm going to. But so strawberries, apples. Maybe we should start with the low-hanging fruit, if you'll pardon my pun, because this again is very adaptive. These kind of grippers are very adaptive to these parts, and they can handle a fairly broad range of parts. The other thing, and we did some tests on this application. Interestingly enough, Safeway grocers here in California have a 14-day bruise test requirement. In other words, any way that you handle the fruit or the vegetable, for 14 days it can't show any kind of bruises from handling it. Well, I've been to some of these vegetable processing plants, and I've seen the operators trying to keep up, and when they start getting away, they do a quick grab, and trust me, they're bruising the hell out of that last tomato. And we think that automation with gentle but firm handling, like electroadhesion fingers here, really excellent. And we passed the bruise test. We did do it, and 14 days later, there was no sign of bruising. Yeah, the problem there is we've been requested that, but if you go back to my slide on electroadhesion, we deposit material on the surface. If the surface is a film of moisture, that's the surface and not the fish itself. So all we are able to do is pick up the moisture and miss the fish. So we tend to stay. Yeah, you can do it vacuum. Yeah.
Most complicated problem with lobsters.
Yeah. So you can use needles and then marinate them after you poke them with the needles. See, value for your needle gripper. And then the other thing I said this morning is we think each picking should start with product classifications. If you could bring all the boxes to one pack-out station, and maybe this is where boxes get packed out. We think this is a good step on how you automate these each pick. So you can see the size. The reason this gripper is so big is we want to be able to handle even big trays and cases, or all the way down to individual different boxes. This one of our early applications for this is in the pharmaceutical industry. Again, e-commerce, people ordering online, off-the-shelf drug and medication. Now I just added this video, by the way, when I saw Walter's video, because this is really interesting. This is one of our first fiber composite sheet handling for the aerospace industry. And what you just saw that Walter showed was how to do it with vacuum. And what you're seeing here is how to do it with electroadhesion. And so and we actually did the same thing. We had the adaptive, more of a passive, I should say, a passive adaptive way of complying to the contours. But you can see here we've got this composite sheet underneath this gantry robot. So what we did on this tool is just push all the vacuum grippers aside and put the electroadhesion in the center, and then we set down. This is composite sheets, so if you look at the carbon fiber bodies, BMW is probably as far along as anybody in the automotive industry here, but the aerospace industry is more and more looking at getting the light, stiff composite materials. And to do that, you have to stack layers of them, and then they go to autoclave ovens, and they get cured and so forth. And it's the stacking of them that is really hard to do with grippers. And so we think it's an interesting application for electroadhesion. Another application, now we're going to switch from gripping with robots to gripping with conveyors. And if you look at these warehouse and these gravity conveyors, you know, everything's changed. Everything used to be so predictable in these warehouses, and now we've got this skew range all over the map. And FedEx Ground is a customer of ours, and they said they have to handle any box that anybody wraps up, regardless of its size and weight. They're stuck with it. They can weigh it and they can profile it when it comes in. But if they just got these roller conveyors and someone's packed a treasure chest, that thing can come flying down this conveyor and destroy itself or harm an operator. So it's a safety issue and a yield issue on these plants. And so what we did at Gravitt, an early prototype, was look at how can we have variable friction knowing the weight of the part. So here you can see this very steep slope that we can vary voltage on, voltage off. So we can slow it down, we can completely stop it, we can slow it down. But if we know what's coming, again, the Internet of Things, we've been told that way back at that weighing station and that structured lighting measure statement, how much it weighed, what was its size, and now we know when it comes, and we know what friction to apply to slow it down down the.
You need to know the friction coefficient, right?
Well, yeah, not really precisely, but yeah, you got to be in the ballpark. And we found another way, which I'll show in a minute, to do this other than these. In fact, this is the. At ProMat, we took a different approach. So here we have parts going up the conveyor at a very steep angle. And then here we put brakes, electroadhesion brakes on gravity rollers, also programmable to either stop it or slow it down, same thing, so that it comes here at a reasonable speed. But here we're going up at 40 degrees, which these boxes would slide down with no electroadhesion. Again, turn the brake on, hold it in place, turn the voltage off, goes to the end, slides over here, and goes up. So this was just a recycling demo that we did at ProMat. And I was scared to death of this because it was a prototype. And you know what the Murphy's Law is of taking a prototype to a show it's going to fail. But it was amazing. This thing ran the entire 3 days of the conference.
I have seen it working.
Yeah, it does work. Yeah.
What's your weight limit of this?
Once again, we're back to what is the surface that we can grip, and then here we also have a little moment issue depending on the height. That's why it's important, for us to know what we're handling. But I can say this: we've lifted 75 pounds when we had enough space. So anyway, I thought it was interesting. So where did this belt technology come from? And Gravitt's roots were back at SRI International. So here, one of the scientists at SRI International is putting dust, talcum powder on the wall to show this. And now he's got this belt robot, basically, a robot with a moving belt. Now he's got voltage on. Now he's going to turn it, and you can see it climbs the wall. even with dust. And the thing that got SRI funded here was started in Japan. The Japanese wanted to inspect the infrastructure of bridges and even buildings, looking for stress cracks and so forth with this kind of product. There's also a big interest in aerospace industry. In the U.S., I believe every 200 flight hours, aircraft have to be inspected. And that inspection is manual and it's very expensive. And when you're doing it, the aircraft's out of use. And so there's an interest in doing that kind of inspection with this technology as well. So at any rate, I promised to get us ahead of schedule. I want to thank these companies for the information that I was able to share with you, and be happy to answer any remaining questions. I think they've had enough of me for one day. Go on.
I have a question.
Yes.
So grasping has similar principles with the fixture in general.
Yes.
Hot technology, have you heard of that PAAW technology? That's also, you showed the SRI proprietary. PAAW is something also I would recommend you. It came out of Penn State.
Oh, okay, I'll take a look. Because fixture is one of our applications as well, just putting electroadhesive pad down and flexible fixturing, having one fixture handle a big variety of parts. Good.
Does the system works in water or with dust?
It works with dust, but the dust will accumulate if you don't clean it off. And we found the easiest way to clean it off is to reverse polarization, and then negatives repel and positives repel. That handles it most of the time, but we think for a lot of really dirty applications, we're going to have a wiping step somewhere where we actually wipe it across a cleansing surface. And then water, we don't work in water. We can work in moist environments. There can even be drops on the surface. We're just not going to be adhering where those drops are. We're going to be adhering, where it's dry.
For the planes, people want to use something like this for the ships. I was asking for that reason if it works in the water to examine the ships.
For shipbuilding or ship inspection?
Yeah.
Yeah, I think as long as we're not trying to adhere to a completely saturated wet surface, that the technology, certainly it's not commercialized today for that, but the technology theoretically should be able to work. It's actually much stronger in vertical, in shear, than it is normal. There's actually a 5 times, because in normal you get peeling. And you can work in normal for light fabrics, but on ships and on wall climbing, you're actually in shear, where you actually have stronger forces.
Pretty nice technology, and it's specifically shear forces is interesting.
Just the opposite of vacuum, right?
Exactly,
Yeah.
This is why we are looking into it.
All right, thank you.
Thank you very much.